Let's start today's tutorial session. So today we will do the tutorial session number 2. So in the last session we have done problems based on the load modeling and load management, and in this today's session we will solve problems based on this demand side management that also comes under the category of load management, and this power distribution system, the structure of power distribution systems. We will see many problems based on the structure of power distribution systems. So let us begin the this tutorial session by solving the first problem, and the first problem is based on the demand side management. And the question first asks about which of the following is an approach for demand side management. Which of the following is an approach for demand side management? And the options are load forecasting, load estimation, load setting, and load shifting. So what is demand side management? Demand side management is an approach implementation done by the utility such that it can just change the electricity usage patterns of the customers. So there are some means by using which the utility change the demand patterns of the customers, and these means are as follows. Means of demand side management, like these are the approaches by which we can change the electricity usage patterns of customers, and these are peak saving or peak clipping, and second one is value filling, third one is load shifting, fourth one is a strategic conservation, and the last one is a strategic load growth and load building. And then maybe others, but these are the main things that we usually done by the utilities for demand side management. So in this question, if we see the options, the only one is matching. That one is D option, load shifting. So this one is correct. And why this load shedding does not comes from demand management? Because it is like curtailment of power, or it is interruption of power. So this does not count in demand side management also. And this load estimation also does not comes in this category, and load forecasting also does not come in the category. So I think you are able to get this point, that in which we can change the load curve. So load the means by which we can the load curve that comes under the category demand side management, and this load setting does not counted because it belongs to the curtailment or interruption of power to the customers. So in this load shifting, if we want to write some points, then in load shifting what happens, we change the power that we shift the power demand from the peak hours to off peak hours. So there is change in the there change in the peak demand, and there change in peak demand, but there is no change in total energy consumption. Energy consumption will remains as it is. So you write here one point for load shifting: reduction in peak demand and no change in total energy consumption. So because we are shifting the load demand from peak hours to off peak hours, and the common examples for this load shifting are deferrable loads. And what do you mean by deferrable loads? That allow time shifting and interruption. Deferrable loads means means the loads that allow time interruption, that allow time shift and interruption. These are not critical loads, like we can shift these loads from according to our convenience. And some of the examples for deferrable loads that what comes under this category, like washing machine. It can be used according to our convenience. That is not necessity to use at a certain time. And EV battery charging, dishwashers. Nowadays, these equipments came in kitchen dishwasher. And just opposite to deferrable loads, we called these the loads as non-deferrable loads. Non-deferrable loads like that does not allow time shift and interruption. And these loads will be like medical equipments or kitchen equipments. If we need food, then we have anyhow to make food in the kitchen. So that are non-deferrable loads. And the most simple example for non-deferrable loads is medical equipments or healthcare equipments that does not allow time shift and interruption. So similarly, for other demands and management, we can write in the terms of peak demand and total energy consumption. Like for peak saving or peak clipping, we clip up the peak some power demands from the at peak hours, such that it will reduction in peak demand, but a reduction in peak demand and also in total energy consumption. That is the difference between load shifting and peak saving. In load shifting, we are shifting power demand from peak hours to off peak hours, but in peak saving, we are just clipping up the power demand. So it also reduces the total energy consumption. So for this peak saving or peak clipping, you can write that reduction in both peak demand and total energy consumption. So whatever the loads that operating at peak hours, we are controlling, we have to control the loads at that time so that it reduce the peak demand. So the examples for this peak saving and peak clipping are efficient control of air conditioners, water heaters, etc. And now this value filling. Value filling is like no change in peak demand but increase in total energy consumption. We are filling up the we are increasing the power demand occurring like we have certain value occurs in the load curve, so we have to increase the load demand at that time. For that, we have to increase the power demand at that time at off peak hours. So for this, you can for value filling you can write that here peak demands remains as it is, so no change in peak demand and increase in total energy consumption. because we are increasing the power demands during off-peak hours. So this there will increase total consumption, and we have nothing to do here in the peak demand. And the examples for this value filling is also electric vehicles charging grid to vehicle. We are taking the power from grid at off-peak hours, so such that power demand happening at valley hours or off-peak hours increases. And the next one is a strategic conservation. Strategic consumption, if we having load curve for certain distribution feeder, so we are having just lowering down the load curve little down, means the whole curve goes down. So in this case, there is change in both peak demand and energy consumption. And what will happen to that? That will reduce because we are shifting down the load curve from a certain height. So here you can write like that: reduction in both power demand and total energy consumption. It is same to peak saving or peak clipping if we see in the terms of peak demand and total energy conservation. Reduction in both peak demand and total energy consumption. And just opposite to the strategic conservation, we are having a strategic load growth or load building. This happens in the case of we having like extend our distribution system, or we having new loads to comes into the picture of distribution system, and we have to feed the power to the new loads or extend our distribution system. For that, this this we need to do the strategic load growth or load building. And the examples for this efficient planning of power distribution. In this case, we are shifting our load curve upwards, not downwards. In a strategic consumption, we are shifting load curve downwards, and in the strategic load growth, we are shifting our load curve upwards. So here you can also write one point that shifts shift shifts load curve downwards. Whole load curves, not at a certain duration of hours. And for the strategic load curve, that is increase in both peak demand and total energy consumption. Increase in both peak demand and total energy consumption. So in this case, we shifts whole load curve upward. Whole load curve upward. If you visualize the figure, then you can clearly get it. So now let us move to the next problem. The next problem also belongs to this load demand side management. In this problem, it is asked about that which of the following devices can be controlled as one of the means of peak saving. For peak saving, or it is also called as peak clipping. So here in this question, it is asked about that what are the means of the peak saving or peak clipping. As we saw in the last problem, By efficient control of air conditioner or water heaters, some of the loads are controllable. By using that, we can reduce the peak demand. Or so for this problem, we are having option air conditioner, water heaters. For this problem, we are having options as A option is air conditioner, B option is water heaters, C option is both air conditioner and water heaters, and D option neither air conditioner and water heaters. So the correct answer will be both air conditioner and water heaters. If we see the load curve, then suppose this is a load curve. So this is the peak demand for this certain distribution system, and we are lowering down this peak demand to a certain height. And this is x-axis is time duration hour. So thus we are just clipping up the peak demand. This one is new peak demand after doing this demand side measurement by peak saving or peak clipping. New peak demand, and this one is old peak demand. So this amount of reduction happens in peak demand. Reduction in peak demand. And uh, we are not shifting this power demand to some other time duration. So this will leads to also decrease in total energy consumption. So this most common example for this peak saving or peak clipping is efficient control of air conditioner and water heaters. And this also does not if we are reducing the peak demand, suppose if we having need of some additional generation capacity to fulfill that peak demand, and if we reduce that peak demand there is no need of that. So this also defer the need of additional generation capacity. So this is the advantage of doing peak saving or peak clipping, that we do not need any more new generation capacity such that we can having fulfill the power demand at peak hours. So this is the advantage of peak saving or peak clipping. Now let us see the next problem. Next problem is that which of the following customers can be called as prosumers? And the options are a customer who participate in demand side management, and B option is customer with rooftop solar photovoltaic generation. C option is a customer who can produce, sell and consume electricity, and D option is a customer who can shift its load demand. So what are prosumers? Prosumers is coined from, if you see this word, it is coined from two terms. Like prosumer. The first pro word comes from producer, and the second, this sumer comes from the word consumer. So consumer only takes power and gives bill, gives the whatever that whatever the charges that the utilities companies uh, takes for giving the power to the customer, that he have to pay. While prosumer is not only taking power from the grid, but in the case if having more power generation from this like renewable sources generation, we are having solar photovoltaic wind, it can sell this power to the utility also. So for this they this requires bidirectional communication or some monetary incentives done by the utilities, such that it motivates customers to install the solar rooftop photovoltaic. Solar rooftop photovoltaic is the most common nowadays, and why this it not consumer is converted into prosumer. And in this figure we can see that consumers takes that unidirectional power flow, consumers takes power from the grid, while in this prosumers it is also generating power through the solar photovoltaic or wind power generation. And this not only takes power from the grid, but in the case of excess power generation it feeds power to the grid, such that it also get monetary incentives and having bidirectional communication with utilities. So if we see these options for this problem number 3, and the option the what best suits for this consumers, the customer can produce, sell and consume electricity, because with the installation of rooftop plants, solar rooftop on the in the houses, not only consumer take power from the grid, but it also sell power to the grid. So that's why a customer who can produce, sell and consume electricity, that are called prosumers. So option C is correct for this problem. Now let us move to the next problem. Question 4 is the flowing busbar scheme does not get interrupted due to busbar faults. This one is nice problem. So we are having different types of busbar arrangement or switchgear arrangements. So these are different types of busbar arrangements or switchgear. You can see say switchgear arrangement. Switchgear arrangement. So for the single bus scheme, we are having single bus bar, and if fault occurs in this bus bars, take the whole substation out of service. So for the single bus bar scheme, if fault in bus bar happens, then the whole substation will be out of service. Whole substation out of service. And this problem number 4 is not a single select question, this is multiple select question having multiple answers. So there more than one option is correct. Now if we see this single bus with transfer bus scheme, so there are two bus bars, one is main bus and other one is transfer bus. And transfer bus is used for the maintenance of circuit breakers. So B option is single bus. It will be more clear if you see the figure belongs to this bus bar arrangement. So in this we are having two bus bars. First one is main bus that is always energized. So it is always energized from the loads are taking power. And the second one is transfer bus, not energized, and it is energized through tie breaker, and it is energized through tie breaker by the main bus during the circuit breaker maintenance. By the main bus during circuit breaker maintenance. So that is the purpose of transfer bus. So it is so transfer bus. It is not used for when the main bus bar is get faulted and transfer bus can feed power to the loads. So for more detail, I just want to say that you refer this lecture number 8 so that there will more clarity, because if you see the figures for this difference bus bar arrangement, it will more visualized easily. So this transfer bus is energized through tie breaker by the main bus during circuit breaker maintenance. It is not used in the case that if one bus is faulted, so from the other bus we can feed power to the customers. That is not like that. So transfer bus is used for the circuit breaker maintenance. And this double bus bar scheme and double breaker scheme both are having double bus bars. Double bus bar scheme. So it is having two bus bars and both are always energized and connected by tiebreaker. So it is having two bus bars. Suppose if fault occurs in one bus bars, then this tiebreaker that is normally open, it is closed and the customers can take power from the other bus bar. So this leads to no interruption in the loads, no interruption in power for the loads. So this is advantage double bus bar scheme. Uh, so that's why it provides operational flexibility. So advantage of this double bus bar scheme, you can write that operational flexibility. Operational flexibility, that you are having possibility to move loads between buses. Possibility to move loads between buses. And the last option is B, double breaker scheme. Double breaker scheme. So in this, one feeder is connected by two circuit breakers. One feeder is connected by two circuit breakers with respective bus bars. So it is having also flexibility of circuit breaker maintenance and also possibility uh, that one feeder is connected by two circuit breakers, so there is no interruption in there is no interruption in power flow if a fault occurs in one bus bar. So both options are correct for this problem number 4. This double bus bar scheme is also correct, and this double breaker scheme is also correct. And this single bus with transfer bus scheme is not correct. Although this transfer bus is present, but this transfer bus is not utilized for feeding power if one main bus is gets faulted. This transfer bus is utilized during the circuit breaker maintenance. So be careful for this option. So this option is not correct. Options double bus bar options are correct. That is double bus bar scheme and double breaker scheme. So let us move to the next problem. Next problem is that a sectionalizing switch is placed in distribution feeder to improve, and the options are voltage drop, reliability, C option is power loss, and D option is power transfer. So if we see this primary distribution system, this is the uh, layout of primary distribution systems. So it consists of three feeders. Let us this feeder 1, feeder 2, and feeder 3. And feeder 2 having just elongated here in the bell manner, and feeder 1, this one is top one is feeder 1 load area, and this feeder 2 load area that has been drawn here in this figure, and the below one is the feeder 3 load area. In this question it is asked about the sectionalizing switch, where it is present this one sectionalizing switch, this one is sectionalizing switch, this one is sectionalizing switch, this one, this one, this one, this one, all are sectionalizing switches. So what is the main purpose of the sectionalizing switch? So first, before that, I just write down the most important point. This during normal condition, sectionalizing switches, it is normally closed. That is during normal condition, it is closed. While on the other hand, tie switches, it also consists of tie switches. Here you can see that between two feeders, the tie switches are present. So tie switches are normally open. In normal condition, it is open. So you can also write this NC, that means normally closed, and NO means normally open. So here we can see that in this figure, sectionalizing switch means like if any fault occurs in this part, suppose in this part any fault occurs, this sectionalized switch will open such that all the powers taken by the other loads that which remain unaffected. So it gets isolated the part only in which fault happens. So sectionalized switch during fault condition, it removes the part in which fault happens. Another parts remains unaffected, and other parts takes power. So you can say that this improves the reliability. And the tie switches are in the normal condition it is open, and during emergency condition it gets closed. Like if we suppose feeder 1 wants to take power from the feeder 2 during abnormal condition or emergency condition, then it gets closed and feed power and takes power feeder 1 takes power from the feeder 2, and similarly feeder 3 can take power from feeder 2, and vice versa, it can also takes power from feeder 3 to feeder 2. So during fault condition what happens, this sectionalizing switch gets open such that other parts of the system remains unaffected, and thus it improves the reliability. Open. And this during emergency condition, like this tie switch once take power from the other feeders, and it also tie switch work to connect the other system from one system. The main task of tie switch is that it connects one system to other system. So during emergency condition, tie switch will be closed, and normally it is open. So this is for this problem number 5. Let us see the next problem. And next problem is that isolator can be operated at. Options are: A option is no load condition, B option is on load condition, C option is light condition, and D option is rated load condition. So we know that isolators are connected just besides these circuit breakers, and both differ by that circuit breaker operates at on load condition. It gets tripping signal from the relay, and behaves accordingly. So circuit breaker on load condition operates at on load condition, while on the other hand this isolator operates at no load condition. If we have to do some maintenance part thing, then in order to confirm that this area should not be energized, this area should not connected to the main system, so the isolator operates during that time. So isolator operates at no load condition. So during maintenance time, we usually operates this isolator. So this oscillator can operate at no load condition. Option A is correct, while circuit breaker operates at on load condition. Next problem is that this is also related to isolators. In a substation with different bus scheme, it is seen that a circuit breaker is kept between two isolators. The isolators are used to protect the circuit breakers from faults, protect the circuit breaker from maintenance, protect the circuit breaker from lightning surge, and the last option is reclose the breaker after a fault. So first option is protect the circuit breaker from fault. It is not like that. The relay gives a tripping signal to the circuit breaker if any fault happens. And this B option is perform the circuit breaker maintenance. Yes, it is correct. For maintenance of circuit breakers, we use the isolators such that after doing this remains unenergized, and we do the maintenance things at that time. If the uh, just uh, isolators just uh, di- uh, isolates the other parts of the system. And the C option is protect the circuit breaker from lightning surge. This is also not correct. There is certain equipments installed at the substation for the lightning surge protection and reclose the breaker after fault. This is also not correct. So option B is correct for this question 7. And the eighth number question is the distribution network topology is usually radial due to. And options are unidirectional flow of power, easy protection coordination, cost effective in construction, and the last is D, all of the above. So we know that primary distribution networks are mostly of radial topology, which results in unidirectional power flow. And if we see our transmission network, how it is, transmission networks are of mesh topology. Mesh means there are various power flow possibilities present. Transmission networks are of mesh topology. Mesh topology means various power flow paths are available. Various power flow paths are available. While in this radial topology, unidirectional power flow happens. Due to that, the radial topology is preferred for its simplicity in construction, cost effectiveness, and protection management. Unidirectional power flow leads to its simple construction, cost effectiveness, and protection management. So all of them are correct. Now let us see the next problem. Next problem is that which of the following will you consider as the most important decisive factor for choosing the permissible length of a ruler distribution feeder? And options are voltage drop, ampacity limit, thermal limit, phase angle limit. So what do you think which of these options will be correct? Ruler distribution feeder means that is low density areas. You can see this one is low load density areas. For high load density areas, this decision factor will differ. Low load density areas. So we see the some important points related to this problem. Primary feeders, primary feeders located in low load density areas are restricted in length and loading by permissible voltage drop rather than thermal restrictions. For low load density area, we look upon the voltage drop rather than thermal restriction because power demand is not that much high or the current demand is not that much high from this low load density areas. While on the other hand, if the primary feeders are located in high load density areas, for example, industrial and commercial areas or metropolitan areas, it is restricted by thermal limitations, not by the not by this voltage drop. So in this question it is asked about the ruler distribution feeder. So the correct option will be A, voltage drop. While for this thermal limitation we will see for high load density areas. So for high load density areas we will take the decisive factor for the choosing the permissible length of feeder. We will see the thermal limitation. Now coming to the next problem. Next problem is that lateral implies to. Options are main or trunk of a distribution feeder, a branch of a distribution feeder, a distribution transformer, and the last option is line insulator. So what do you think the correct option for this problem number 10. Now, if we look on this picture, then this one is the primary main feeder. This one is primary main feeder. And this fuses, this one, this figure denotes everywhere transfer fuses. Wherever the transformer is connected, the first it is connected to its fuse. So transform fuses are present along with the distribution transformers. And laterals are the branch of distribution feeder. So these are, this one is lateral, this one is lateral, this one is lateral, this one is lateral, that is connected to the primary main feeder. This one is lateral, and the sublaterals that are connected to further laterals. So this one is connected to one of the lateral. So these are sublaterals. So this one is connected to a lateral. So these are sublaterals. These are sublaterals. And lateral is also connected to somewhere. This one, like see, fuses are connected. So this is lateral fuses. So if we want to write that, we can say that if we are having main feeder, main primary feeder, and suppose this feeder, let us say it is connected to a, let us say it is connected to three laterals. So further it is connected through lateral, lateral, lateral feeder, and then it may be like that each lateral having several sublaterals. Suppose lateral one is having two sublateral. So it is having also sublateral, and then suppose it is having second lateral is having three sublaterals. Sublateral. So this hierarchy follows. Like first the distribution feeder is connected to substation, and then we are having these laterals, and then finally these are sublaterals, and these, and then we are having distribution transformer. And distribution transformer can take power from any of one of them. That is, it may be connected to the main feeder, it may be connected to the lateral, it may be connected to sublateral. So this is the thing for this problem number 4. So the correct option for this question 10 is a branch of a distribution feeder. Now let's move to the next problem. Next problem is that depiction of fault location is fill in the blanks indoor substation than that of in outdoor substation than that of indoor substation. Options are easier, difficult, same. So this one is very easy question. I think you all able to get it easily. So now if we see the difference between this typical outdoor and indoor substations, then in terms of space, outdoor substation having more space required than the indoor substation. And this cost is outdoor substation cost is cheaper than the indoor substation. So this leads to the profits is huge. So indoor stations substation is expensive, that leads to that leads to less usage or frequently we did not see indoor substation, while on the other hand outdoor substations are costly. But we may have to uh, install or may have to just land up this indoor substation because there is some community problem or we are having less areas, so that we may require to we may require to build up the indoor substations. But generally in the common case we have to generally see this outdoor substation only because this one is cheaper. So this is the most economical factor, cheap factor is the that we more frequently use to see this outdoor substation. While this maintenance for this outdoor substation is more because this is more for fault prone, while this indoor substation this requires less maintenance, and this is also just fully fully insulated or fully covered in a area, so this will not lead to fault due to some like animals uh, or natural things. So this requires less maintenance. And this fault location and this detection of fault location is easier in outdoor substation than this indoor substation. Why this happens? Because the equipment is in full view. Because the equipment is in full view. We can easily see the all equipments. While it is covered in indoor substation, it is covered. So the equipment is enclosed, so it is difficult because the equipment is enclosed. So that's why it is difficult to locate the fault in indoor substation. And reliability, ABC reliability, outdoor substation is less reliable than indoor substation. So for this problem number 11, the correct option is easier. Now let us see the next problem. Next problem is that which of the following tariff structure is considered as a block meter rate structure? So utility takes some charges for taking power from the customers, and there are different tariff structures. As we know that uh, some of them are flat demand rate structures, that is a constant price per kilowatt hour. As the energy consumption increases, this price just same as it is for every unit of energy consumption. And while on the other hand, block meter data structure that it lowers down the prices for greater usage. And this demand data structures there is separate charges for demand and energy. That means that separate charge for kilowatt and separate charges for kilowatt hour. While for season data structure, higher prices per kilowatt hour used during the season when system peak demand occurs. And the last one is the time of day or peak load pricing structure. Higher prices per kilowatt hour used during the peak period of the day and lower prices during off peak period of the day. So these two are season rate structure and time of day structure or peak load pricing structures belongs to the category of the reduction in peak demand. So motivates the reduction in peak demand because at peak hours they are taking the higher prices. Like if any season the power demand increases, then at that season higher prices is taken by the utilities. So season rate structure for the season and the time of day structure for a certain period of time in a day. Higher prices per kilowatt hour during the peak period of day and lower prices during the off peak period of the day. Now, if we want to just understand this, how this uh, block meter it a structure works, so we can visualize it using the graph. Like suppose y-axis belongs to charges taken by the utilities in rupees. So for some duration, for certain unit consumption, it is having a fixed rate. So this one is block 1, and for the next unit consumption, this slope reduces. So let us take this block 2, and for the next, again the slope reduces. Let us take this as block 3, and x-axis denotes this units consumed, kilowatt hour. So let us suppose that block 1, the utilities are charged first 50 units or first 50 units are charged at the rate of rupees 5 per unit. And for this next block 2, for next 40 units, it is charged at rupees 4 per unit. And for block 3rd, for next 20 units, it is charged at rupees 2 per unit. So this denotes the block rate structure. And suppose there is no change in slope, then it tells about the flat demand rate structures. While on the block meter rate structure, the prices will gets lowered down for the greater usage. So this is not I think for energy consumption point of view, this motivates the customers to use more power, because after 50 minutes its prices gets lowered down, so customers gets motivated to use more power because the price has been reduced. So for this question, the correct option is that B, lower price for greater usage. Block meter rate structure denotes that lower prices for greater usage. Now let us see the next problem. Next problem is that which of the following is a decision factor for the conductor size selections? Options are physical barriers, substation capacity, conductor rating, feeder limitation. So if we see this figure, the conductor size selection depends on the voltage drops, transformer rating, conductor rating, total cost, power losses, load growth rate, load forecast. The physical variance is not a decision factor for conductor size selection. Substation capacity also does not encounter this. Conductor rating, of course, this conductor rating is a decision factor for the conductor size location, and feeder limitation also does not is a decision factor. Correct option will be C, that is conductor rating, which is a decision factor for the conductor size selection. 14 number problem is that which of the following is not a substation equipment? Power transformers, yes, it is a part of substation equipment. Current transformers and potential transformers are also part of substation equipment. Current transformers and potential transformers. Circuit breakers and isolators is also part of this substation equipment. Circuit breakers. Water reservoir is not a part of substation equipment. It is present for the thermal power plant. So the correct option is D, water reservoir. So if we see this typical substation may include the flowing equipment, power transformers is present, circuit breakers and isolators are present, station buses and insulators are present, that is bus bars, current and potential transformers are present, shunt capacitors are present for improving the power factor, grounding system is present, lighting arresters or gaps are present, protective relays are present, station batteries are present. If you visit some substation, then you can see that batteries are also present for providing the power to the automation and control unit that present at substation. So battery system is also important part of each substation. So many of you are having doubt that why these batteries are present in substation. These are present to feeding the power. There are various automation and control units present at the substation. So these battery used to feed the power to that automation and control unit present at the substation. So this is all about for this theoretical type of question that belongs to demand side management or typical structure of a primary distribution system. Now let us be see the one problem based on the assignment 2 in which many of you having problem in finding out the contribution factor. How to find out the contribution factor if we are having different classes of load are given. So I have taken out this question number 15 from that assignment number 2 from the currently running assignment. So let us read the question. There are three different types of customers connected to feeder. The load demand data for a typical day is shown in a table. The connected load for lightning load is 150 kilowatt. Total connected load for the commercial and residential customers are 1600 kilowatt and 2250 kilowatt respectively. So here in this table we can see that there are three different classes of customers, the three different types of loads present connected to a feeder: lightning load, commercial load, and residential load. And for different each hour, how much power demand is occurring through this demand and through different types of loads is given in this table. So from starting from the 12 a.m., that is in the midnight, it is given in this table, and it goes like here 1 a.m., 2 a.m. accordingly. And the next slide it continues till in the midnight 11:59. So for whole day, the demand from the lightning load, commercial load, essential load, it is given in this table. So let us see the next first problem. First part of this question 15 problem is that, so determine the load factor for lightning load. So we know that load factor is, we know the formula of load factor is that it is the ratio of average demand to the peak demand. Ratio of average demand to the peak demand. And this we all know familiar. This is very important formula. I think we all are familiar with this. We have used so many times. So for finding out the average demand, first we will find out the unit consumption for the lightning load for whole 24 hours, and next what we will do, we will divide that unit consumption for whole 24 hours by number of hours, that is 24, and from there we will get the average demand. So write like that: units consumption during 24 hours. So let us see for lightning load how this table, how this varies. For lightning load, we can see that 50 kilowatt, starting from 50 kilowatt for 1 hour, 2, 3, 4, 5, 6, 7. For 7 hours, lightning load demand is 50 kilowatt. So 15 to 7, that will give 350 kilowatt. And for next 0, how many times? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. For 0 kilowatt demand is for 11 hours. And the next again 50 kilowatt for 1 hour. And next 100 kilowatt for 1 hour. And next 150 kilowatt for 4 hours. So let us verify this. 7, 11, 1, 1, 4, 7, 11, 18, 18 plus 2, 20, 20 plus 4, 14. It is correct. So just do the simplification. So 3 is 50 plus 0 plus 50 plus 100 plus 150 into 4, that will give you 600. So it will 350 plus 50, 400 plus 100, 500 plus 600, that is 1100 kilowatt hour. That much amount of unit is consumed by the lightning load during 24 hours. And next we will find the average demand. Average demand will be units consumption units consumption divided by time in hours. Time in hours. Unit consumption is 1100 kilowatt hour divided by 24 hour. So it will give you the average power demand as 45.83 kilowatt. Next we have to find out the peak demand for residential load. So peak demand for residential load we can see in the table, sorry, lightning load, we can see in the table it is 150 kilowatt. So it is 150 kilowatt. Therefore we can find out the load factor, that is average demand 45.83 divided by 150. So it will give you 0.3055 answer. So the option C is correct. Next we will see the part 2. Determine the demand factor for residential load. We know that demand factor is maximum demand divided by demand factor is the ratio of maximum demand to the total connected load. So maximum demand for residential load, it is asked about the residential load. So for residential load we are having maximum demand. We can see in the table what is the maximum demand for residential load. So it is 200, 200, it goes till here 350, 350, 1200, 1200 it goes till here 1400, 900, 750. So maximum demand is it is residential load. Sorry, it is asked for residential. So if you look this last column, 600, 600, 150, 150, 300, 300, 500, 550, 600, 750, 850, 900, 1200. So this one is the maximum demand. 1200 is the maximum demand for residential load. So maximum demand is 1200 kilowatt and total connected load is given in the problem. Total connected load we are having given as total connected load given as for residential customer 12 2250 kilowatt. 2250 kilowatt. Hence, we can find the demand factor maximum. It is the ratio of maximum demand to the total connected load. So it will give you 0.533. So option B is correct. Now let us see the most important part of this problem. It is asked about the country, country determine the contribution factor for commercial load. So we know the formula that aggregate or group maximum demand will be the contribution factor for each class. Like here contribution factor for lightning load or peak lightning power demand plus commercial contribution factor of commercial load and this peak demand for this commercial load maximum demand plus contribution factor for this residential load and thus peak demand for this residential load. We all know this formula how from there we can relate the aggregate peak demand or group peak demand or coincidence peak demand. So this is called as group peak demand or aggregate peak demand or coincidence peak demand. Coincidence peak demand. So we can tell this is aggregate group demand, aggregate peak demand, and these are this one are non-coincidence peak demand. Back it is separated for each type of loads. Non-coincident, non-coincident peak demand. For different classes of customer or for different classes of loads, they are having different maximum demand from the utilities. And while for the feeder, it is having different peak demand, as we will know this concept. So here in this problem, there are three unknowns contribution factors. This one is unknown. Contribution factor of lightning load, contribution factor for commercial load. This one is unknown. Contribution factor for residential load. This one is also unknown. So by using this formula, we cannot find because there are three unknowns. And this group peak demand we know this for commercial load what is the maximum demand we know commercial for lightning load what is the maximum demand we know and for the residential load we also know the maximum demand how much is the maximum demand for this residential load and we don't know this contribution factor. So for that we will use the another formula that is class contribution factor. class contribution factor, that is the ratio of class demand at time of system peak, at time of system peak, at time of system peak to the class non coincidence, class non coincident, non coincident maximum demand or peak demand. So for using this formula, we can find out the contribution factor for different type of loads. So for this formula, we know that we need to find out the aggregate peak demand. So top numerator is that class demand at time of system peak. So first we need to find out the aggregate peak demand or group peak demand. So let us find out the group peak demand for different hour of for different time duration. So group peak demand, and the unit is kilowatt. So we can uh, find out that for 50 plus 200 plus 150, 400 kilowatt, 400 kilowatt. This one is also 400 kilowatt. This one is also 400 kilowatt, and this one is also 400 kilowatt. And now it will change it to 300 plus 200 plus 50, 550 kilowatt, 550 kilowatt. And now this one is also 550 kilowatt. This one is 650 kilowatt, 300 plus 350. This one is 850, 850. This one is 1750. And here group peak demand, group peak demand kilowatt. So here it will give you 1800, here 1800 again, and for this duration 1800, 1800, 1800. Now it is 2000, it is 2150, it is 100, 850 plus 50, 900 plus 900, 1800. This one is 1900 plus 750, 97, 16, 1750, 1750. This will give you 1200, 1900 plus 2500, 2050 plus 1850. This will give you 1350. This will give you, last one will give you 100, 1100. So we have to find out the aggregate peak demand. So this one is not peak demand. We have to look from this table that how much will peak demand happening. Group demand kilowatt. What is the maximum demand for the feeder? Group demand. So if we see the group demand or aggregate power demand, then what will the maximum starting? We will see from the starting 400, 400, 550, 650, 850, 1750, then 1800, 2200, 2150, and lower down 1800, 750, 250, 1850, 1350, 1100. So this one is the group peak demand 2150 for the time duration of 5 o'clock to 5:59, that in the evening hour. So for this duration, this one is the aggregate peak demand of the feeder. So just highlight this row. So this one is the aggregate peak demand at this time duration. So we have find out the time at with the class at with the system peak is at with the peak demand of system occurring, that is 5 o'clock in the evening, 5 o'clock to 5:59. Now we have to find this class contribution factor. Suppose we have to find out this. Here in this question we are having find out the contribution factor for this commercial load. So for commercial load we have to find out the class demand at time of system peak. So at the time of system peak we can see that commercial load is taking power, is demanding power of 1400 kilowatt. So here it will 1400 kilowatt divided by class non-coincidence maximum demand. That means for that commercial load, what is the maximum demand? What is the peak demand for the commercial load? For the commercial load, maximum demand is 1400 only. So it is same as it is. So 1400 kilowatt. So it will give you 1.0. Similarly, we can find the contribution factor for lightning load. So first we need to find out the power demand at the time of system peak. So power demand at the time of system peak is 0 kilowatt. So numerator is 0 kilowatt and class non-coincidence maximum demand is it is 150 kilowatt. So 150 kilowatt it will give you 0 0.0, and we can also find similarly the contribution factor for residential load. So the power demand during the system peak for residential load is 750 kilowatt. 750 kilowatt, and the maximum non-coincidence maximum demand for the residential load is 1200 kilowatt. 1200 kilowatt, it will give you 0.625. So for this problem we need to find out this contribution factor for commercial load. So it will be 1.0. Option D is correct. Now we can verify this whatever the contribution we have founded out using this formula with the first formula, that is this one: aggregate peak demand is equal to the contribution, it should be multiplied with the contribution factor of respective load with the peak demand of that load. So we can verify the answer as aggregate maximum is equal to C light contribution factor of lightning load, maximum demand of lightning load, plus contribution factor of commercial load, plus contribution factor of residential load, plus maximum demand of residential load. So we know that aggregated, so left hand side we have aggregated maximum demand, that is 2150 kilowatt, and RHS we having Lightning, for lightning load contribution factor is 0.0 into lightning max is 150 plus contribution factor for commercial load is 1.0 and maximum demand for commercial load is 1400 plus residential load 0.625. Maximum demand for residential load is 1200. So it will give you 1400 plus 750 kilowatt. So it will come out as 12,150 kilowatt. So LHS is equal to RHS. Hence it is verified. So for finding out the contribution factor for different classes, we have followed two steps. So I just write to mention it here. Calculation of contribution factor. Two steps you have to follow. First, you calculate the aggregate peak demand. Find out the aggregate or group or coincidence aggregate peak demand. Sorry. Find out the time instant at which the aggregate of peak demand is occurring. Find out the time instant at which find out the time instant at which aggregate or group peak demand is occurring. And next we will, for finding out the contribution factor of different classes, we will find out the power demand at that time instant for that class, and it will be divided by the peak demand for that class. So we will use this formula, class contribution factor class demand at time of system peak, class demand at time of system peak. Here in this question it is given as feeder peak at time of system peak divided by the class non coincidence maximum demand, non coincident maximum demand. So don't confuse with these terms like class what is. So based on the customers, based on different types of class, different types of load, it will vary. So the you should just understand the fundamental what is happening. So if you are having given the table, and from the table you have to find the contribution factor for different classes or for different kinds of loads or for different kinds of customers, then you need to first find out the aggregate or group peak demand, and then in the next step you have to find out the time instant at which this group demand is occurring. And finding out the time step, you need to just put this formula where you have to know that the power demand at the time of uh, uh, power demand at that time instant, and it should be divided by the aggregate, it should be divided by just use this one. I hope it is clear to all of you. So this is all for today's tutorial session, and we will meet in the next tutorial session on the next Saturday at the same time at 4 o'clock. Thank you all for joining the session. Have a nice day.